Okay. Good afternoon, lads and ladies. My computer's telling me I'm having some problems with audio. And in addition to that, I came down with a nasty respiratory infection over the weekend. So I'm speaking a little more softly than usual, which I understand is already a little bit soft. So if you have any trouble hearing me at any point today, please just type in chat and let me know. Today we have a few things to talk about. One of them is the exam, which we're going to have to move. I'll go over the reasons why. Another is the storm. So apparently, I trust all of your phones did the same thing in the last hour that mine did, where you got a push notification, you got an emergency notification, you got an email, and you got a phone call, all from Santa Fe letting you know that the school is closing early today and will remain closed tomorrow due to the tropical storm that's making its way through the area. So we're gonna have to deal with all these things, but that's okay. It's gonna be all right. Don't panic. Have a backup plan. So here we go. This is MAC1140 pre-calculus. It's a lecture. And today is the 6th. So, yeah, again, excuse me if I sniffle, blow my nose, and that stuff. I apologize. I'm still getting over this thing. So last time we talked about transformations of graphs. Today I want to get a little more practice with that. And then there's two other sections that we want to address. Combining functions, which is 2.7. So transformations is 2.6. Combining functions, and then one-to-one functions and inverses. Those are the topics that we're supposed to complete before exam 1. 2.6, and then we certainly will finish this. I think we're going to get through all of this. We will not be finishing this today. And since we're losing Wednesday altogether, having already lost Monday of this week to the holiday, there's no way for us to do a fair test this Thursday. It's not right. So the other thing we're going to need to do is talk about rescheduling the test. I'm trusting that the storm is not going to be devastating, that the storm may take down some power lines, may cause a little bit of flooding, but Gainesville being far enough inland, I don't think that the school is going to be closed on Thursday. It's maybe even foolish of them to close on Wednesday, but that's not for me to say. So I think today we will wrap these topics up nice and neat. On our next opportunity to meet, we will be able to go through this. We may spend the whole class period on it. And then the following class period, we will have our first test. So instead of having exam 1 this Thursday, we will have it next Monday. And what I am going to do is publish a new homework set and a quiz. So there will be at the start of class Monday. So let me remind you and a little bit myself what we have up in WebAssign right now. I don't think I had a homework set. Oh, we did have a homework set due Monday. Did I have a homework? What the fuck was a homework set due for you?
No, there's due Wednesday.
Just Wednesday, nothing Monday?
I think Monday was like last week. So you gave us a full week to do it.
Right. Okay, good. Yeah, that's what I remember. So you do have a homework set that is due on Wednesday of this week. That's this guy, right? Homework 2. 7-7. Yeah, okay. So here's what I'm going to do. I'm going to upload one more homework set for you guys and one quiz, and those quiz will be due next Monday at the start of class. That homework set will contain the material here that's not on the previous homework, but is on the test. So combining functions and one-to-one functions and their inverses. And then the quiz is going to cover all the material that's on the test. So you can kind of think of the quiz as like a pre-test or proto-test. Don't wait, obviously, until Monday to try and take that. Take the quiz. So I could make it due sooner, but I know it would cause trouble. So please attempt the quiz no later than Thursday. That's Thursday. This Thursday, which is going to be 7. That way, if you have things that are driving you nuts, things that don't go well, you can come by my Thursday office hour and we can talk about it. You have time to study over the weekend. Think of the quiz as a tool to help prepare you for the test. Any questions for me about the kind of rescheduling stuff?
So tomorrow we have no class.
Yeah, unfortunately, the college is closing, and they said we're not allowed to do any teaching, even though it's an online class, because people's power may be out, and so you, in theory, may not be able to connect to the internet, and that would mean I would be excluding people based on that. So, yeah, we're not allowed to have class tomorrow. Any other questions?
I have a question.
Yeah, Bianca.
So, the quiz is due on Monday, and you said no later than Thursday. Why can't we do it like on a Friday or?
Oh, well, so Thursday is the last. Here's the thinking. The last office hour I'm going to have before your exam next Monday is this Thursday. So I would really like it if you attempt the quiz before 3 p.m. this Thursday. That way, if you have trouble with any problems, you can come talk to me in my office hour on that day and I can help you out. And that way you're getting something out of the quiz. You're like, oh shit, this problem. If this showed up on the test, I'd be in real trouble. I better come to the office hours and ask him about that. If you wait until Friday or Saturday to try the quiz, you're not going to have that chance to come to office hours and talk with me before the test. But there's no grade penalty or anything like that. It's just a strong suggestion to attempt the quiz before 3 p.m. on Thursday.
All right, perfect. Thank you.
Of course, of course. Any other questions about the kind of bookkeeping stuff here? All right. So last time we talked about transformations of graphs, and I showed you guys how to do the 4 fundamental transformations: the horizontal scaling, the horizontal shift, the vertical scaling, and the vertical shift. We learned that specific kinds of scalings are reflections. So you can flip over the y-axis, that's a horizontal reflection. You can flip over the x-axis, that's a vertical reflection. I want to talk about some special kinds of functions that are invariant under some combinations of those transformations. And these are called even and odd functions. So this is section 2.6 continued. Specifically, we're going to talk about even and odd functions. If you want to refer to those things in one word, the word for even and odd is parity. I'll just give you the definition. The function f is called even if f of negative x is the same as f of x. And this is associated with even functions. Even functions graphs are symmetric about the y-axis. And if you think about it in terms of transformations, that's actually here in the algebra. F of negative x, if you think about the graph of f of x itself and the graph of f of negative x, what kind of transformation do you need to apply to the graph of f to get the graph of f of negative x? What sort of transformation would this be? Anybody remember? Kind of forget about this part for a minute. Just look at this part. What sort of transformation is this?
Would it be a shift on?
Now remember, adding and subtracting inside gives you a horizontal shift. So
is it the horizontal scaling?
it is. It's a particular kind of horizontal scaling. Does anybody remember what particular kind of horizontal scaling we're looking at there?
A reflection.
Yeah, it's a horizontal reflection or a reflection over the y-axis. So when we say that f of negative x is the same as regular old f of x, we're saying that when you reflect over the y-axis, nothing changes. And that's the same thing as saying that you're symmetric about the y-axis, isn't it? Now, on the other side here, the other side of this coin, the function f is called odd if f of negative x is equal to negative f of x. And odd functions graphs don't worry, I'll draw you pictures in just a minute. Plural possessive functions apostrophe. Odd functions graphs are symmetric about the origin. So this guy right here, back in the definition of even function, said f of negative x is the same thing as f of x, which means when you look at the graph reflected over the y-axis, you get the same shit as the original. In other words, the graph is invariant under reflection over the y-axis. You flip over horizontally, flip over the y-axis, nothing changes. This says something slightly more complicated. This says if you flip over the y-axis, if you reflect horizontally, that's the same as doing this transformation. What is this transformation?
A vertical reflection.
Yeah, this is a vertical reflection. So the algebra of the odd function definition here says flipping over the y-axis or doing a horizontal reflection is the same as flipping over the x-axis or doing a vertical reflection. And if you do both of those, that's a symmetry about the origin. Some pictures will help here, but that's kind of the nice way to really understand these things in terms of the geometry. Is that these definitions are encoding transformations. And the fact that these things are equal to each other, we're saying that those graphs, the original graphs, are invariant under those sets of transformations. So just a slightly more grown-up way to think about it than we do in earlier algebra classes, that's all. Some examples. The function f of x equals x squared plus 1. First off, how do I get this graph? What's the parent function?
X squared.
And what do you do to the parent function in order to get the graph of f of x here?
You go up.
Apply the transformations.
Yeah. We specifically, what transformation do I need to apply to x squared to get this guy?
Up by 1.
Very good. Yeah, up by 1. So here's the graph of x squared plus 1. We know on the graph here are the points 0, 1. You can call this guy over here 1, 2. And call this guy over here negative 1, 2. All right, there's a nice graph. Remember the rules? I know 3 points. When I ask you to graph a function, whether using transformations or something else on a test, I'm going to require you to plot 3 points. All right, so here's my graph. Do you notice any symmetries? If I take this guy and go, does he change?
Nope.
No. So this function has a graph which is symmetric about the y-axis. And remember what that means. That means doesn't change when reflected horizontally. Or over the y-axis. And that's one way to detect whether that function is even or odd. I would say, therefore, f of x equals x squared plus 1 is an even function. But that's not the only way to check that this is an even function. We can check the definition of even function. Remember that definition? That was that f of negative x is equal to f of x. So if I ask you to check using the definition or check algebraically that a function is even, means you need to show that this is a true statement for that particular function. Here, f of negative x is negative x squared plus 1. Right? Remember, f of dog shit would be dog shit squared plus 1. F of anything is that thing squared plus 1. So here, f of negative x, I just take the x in this formula and swap it with parentheses negative x. What I want to do is show that this is the same thing as f of x. How would I go about doing that? How can I simplify this expression down here?
You can take away the negative because when you square a negative, it becomes positive.
Yeah, the negative is inside the parentheses there. It's all being squared. And what Ainsley said is correct. When you square a negative, it becomes positive. If we want to be really careful about it, negative x is the same thing as negative 1 times x. So this is negative 1 times x all squared plus 1. And then following your rules for exponents, you know that if you take a product of two things and you raise it to a power, a times b all to the n, this works for products, that's a to the n times b to the n. So negative 1 times x all squared is negative 1 squared times x squared. And then we still have our plus 1 over here. And negative 1 squared is 1. This is 1 times x squared plus 1. And 1 times x squared is x squared. So this is just x squared plus 1. And x squared plus 1, that's the original function, right? That is f of x. So I can come down to this line, I can say, oh shit, yeah, this is f of x. So I've shown that f of negative x is the same as f of x. So you can check if a function is even or odd by drawing the graph and looking for the appropriate symmetry. Or you can check whether a function is even or odd algebraically by verifying using rules of algebra that the definition of even or odd is satisfied by that function. Questions on either of those approaches here? Sorry to do this. All right, one more example like this. What's a fun one? We haven't talked about rational functions yet, really, have we? But we're going to. Maybe it would be more fun to explore. So I'd like to know whether this function is even, odd, or neither. Functions don't need to be even or odd. They can definitely be neither of those things. Now this one you don't know how to graph yet. The only kind of odd functions that you do know how to graph are somewhat boring. So I want to give you something a little more exciting. So since you don't know how to graph this, what would we want to do?
Check it algebraically.
Yeah, right. We want to verify the definition. So we want to check if one of the definition of even is f of negative x equals f of x, odd f of negative x equals negative f of x. Check if one of those is true. And you'll notice they both start with f of negative x. So in both cases, if you're checking algebraically, you're going to swap x for negative x and kind of see what happens. If you're able to simplify the result back to the original, it's an even function. If you're able to simplify the result to the negative of the original, then that's an odd function. So in either case, we've got to look at f of negative x and kind of see what happens. Here, f of negative x is negative x divided by negative x squared plus 1. We all agree that that's what f of negative x is? So everywhere there's an x, I'm swapping it for parentheses negative x. And kind of conveniently, the downstairs here is the thing that we simplified on the last example. So upstairs, parentheses negative x without any powers or numbers out front, that's just negative x. And then downstairs, negative x all squared, we saw that that is x squared. So negative x all squared plus 1 is x squared plus 1. And then having a negative upstairs is the same as having a negative out front. This is the same as negative x over x squared plus 1. And the kind of algebra rule here, if you like, is that negative a over b, like this, is the same as negative a over b. And then this piece you recognize as the original function. That's f of x. So this piece, this is negative f of x. So what kind of function is this?
Odd.
Perfect, it's an odd function, right? We were able to show that f of negative x is equal to negative f of x. Now let me show you what the graph of this looks like. This is a cool graph. I'm going to teach you how to graph this function when we get to the section on rational functions. But for now, just tuck it into your notes. This function has some asymptotes. Really just one asymptote. That's a term you may have heard in college algebra or elsewhere. It also has some mins and maxes. Ooh, am I doing this backwards? I think I'm doing this backwards. Sorry. Started to put those points in the wrong spot and didn't realize it until just a second ago. Here we go. This is what the graph of this function looks like. Ignore these 2 points. It's a nifty function. And if you look, you'll see a certain kind of symmetry to the graph here. Ignore this. When we say a graph has origin symmetry, what we mean is if you take a point on the graph, like for example, this point over here, and you reflect it through the origin, you will land at another point on the graph. And it's the same thing as saying if you were to fold this over here and then fold it down, that you land back on the graph. So this is what origin symmetry looks like. Another example of a graph with origin symmetry is 1 over x cubed, the cube root of x. Let's look at that. This is also origin symmetry. What else? Let's say 1 over x. Also has origin symmetry. Also has asymptotes. Of course, x cubed itself has origin symmetry. Who else? There are plenty of polynomials with origin symmetry. And just good old-fashioned x cubed. These graphs all have origin symmetry. This would be x minus x cubed. All of these have origin symmetry. And all of these are odd functions. So you can kind of see what I mean when I say you take a point on the graph here, reflect it through the origin, you get another point on the graph. Point on the graph here, reflect it through the origin, you'll get another point on the graph. That's what we mean by origin symmetry. It's a little more complicated than y-axis symmetry, but it's not anything crazy. And I think y-axis symmetry is so straightforward. Probably you don't need to see a bunch of examples of that, right? Would we like to see some more examples of functions with y-axis symmetry, even functions?
Sure.
And this will conclude our function transformations. So x squared, of course, and any vertical translates of x squared, like x squared plus 1 or x squared minus 5. This guy, symmetric about the y-axis. Things can be a little more complicated though. So he ended up a little asymmetric, but dip went down a little too far on the right. But you get the idea, this guy. 1/x². Who else found this in here? I mean, there's so many other examples we could use. No trigonometric. Yeah, here's some more functions with y-axis symmetry, or even functions. Okay. 1 second. You okay, buddy? All right, buddy. Sorry, I have a sick dog. Yeah, so I'm pretty satisfied with our cover of 2.6. Are there any questions from transformations that you guys would like to look at more carefully? Anything that's kind of bothering you? Anything you're nervous about? So we have our 4 transformations. Remember to apply them in the correct order. Horizontal stuff before vertical stuff, and then within that, always scalings before shifts. The next section, 2.7, is on combinations of functions. There are a few basic algebra rules that will allow us to take 2 functions and kind of glue them together to get a new function. Most of these are pretty straightforward. So given 2 functions, f and g, one can form new functions. With some pretty evocative names like f plus g. And the way I would form the new function f plus g is by telling you what it does to x. And it does the kind of obvious thing, f plus g of x. I call it that because the way we define it is by adding f of x to g of x. Mathematician is not very creative in this naming scheme. And then each of the other algebra operations has an associated, new function combination. So I could create a new function, call it f minus g, by saying what it does to x is you take f of x, and then you subtract from that g of x. I could create a new function called f times g, and say, okay, well, f times g of x is f of x times g of x. And if I want to create a new function called f over g of x, or f over g, the way I do that is by taking f of x and dividing it by g of x. Before we go further, I want to talk about the domains of each of these. So imagine I know the domain of f and I know the domain of g. What might be the domain of f plus g? Purely in abstract. Yeah, sorry, Mason.
All real numbers.
Well, if both f and g have domains all real numbers, then yeah. But suppose A is the domain of f and B is the domain of g. Then what do you think might be the domain of this first guy in terms of A and B? So maybe A isn't all real numbers. Maybe A is just like some interval. If I'm going to plug an x value into here, I have to be able to plug it into here, and I also have to be able to plug it into here. So if I take a number that's in the domain of f, but is not in the domain of g, can I do that?
You have to have the same common denominator.
Not necessarily anything with denominators. Suppose, for example, that the number 3 is in the domain of f, but 3 is not in the domain of g. Can I plug 3 into this first function?
No.
No, right? F of 3, I could do that, but g of 3, I couldn't do that because 3 isn't in the domain of g. So in order for me to be able to plug an x value into this first function, it has to be in the domain of both functions. Does anybody know the set operation that says take what's common to both sets?
X.
There's a special name for it. The domain of f plus g here would be the intersection. In other words, the domain of this function is the overlap of the domain of the two different functions, f and g. And that's true for all three of these. All of these have that same domain. What we're saying here is that to plug an x value into any of these, we must be able, it has to be in the domain of both. The domain of both f and g. The rule down here is slightly different. And then there's two more different operations I'm going to show you, and they have completely different domain names. If I want to plug an x value into this, I need to be able to plug it into f, and I need to be able to plug it into g, but something additional must be true. So in addition to this rule, what else must be true for this function? Imagine you're going to plug a number into this function. Upstairs here, you got to plug it into f, which means that number needs to be in the domain of f. Downstairs here, You're gonna have to plug that number into G. So that number better be in the domain of G. But what else do we need to be true about the downstairs?
It can't
And
be
0.
Very good, cannot be 0. So the domain here, the domain of F over G, slightly more complicated. This would be A intersected with B, and then you've got to kind of throw away, or write it as a minus, numbers that make G of X equal to 0. That's the idea. So you take the commonality between the domains of F and G, but then you also throw away anything that makes the bottom 0. Now, if these rules look intimidating to you, don't stress too much. In practice, you don't really need to think about them this way. I'm just trying to get you guys to think about sets. Turns out pretty much all mathematics is built on set theory. Now, the last two operations we're going to define on functions are called composition. These are all well and good. But the real good shit here are the functions f of g and g of f. You could also look at f of f or g of g or any other combination like that. It's really just this little operator in the middle here that I'm trying to define. It's an open circle. The LaTeX code for it is /circ. If you're trying to type it in WebAssign, you'll hear me call it f of g, because the rule is f circ g of x is f of g of x. You plug the one function into the other. And the other guy, you just do it in the other order. G circ f of x would be g of f of x. And here the domain rules are totally different. In fact, they're actually kind of hard to write down in terms of the sets, like I did above. I'm not even going to try here. Domain rules. Domain rules here are more complicated. One thing we can say for sure is that the domain of the composite function has to be a subset of the domain of the inner function. Because really what's going on, if you want to plug an x value into this guy, first you plug that into G, then you take the output from that and plug that into F. So it'd be the subset of the domain of G such that the output there is in the domain of F. It's a little complicated. But I'll show you some diagrams. First, let's do a couple easier examples. Again, these are kind of like toys. Think of these as like practice BB guns, because down here's your M16. This is the thing we actually go to war with. This is the thing we play with to get comfy with that. So these things up here, obviously the definitions are kind of trivial and silly, but the idea is to get you comfy with the notation, the concepts, so that when we start talking about composite, the composition operator at the bottom, you won't be quite as intimidated with the style of questions we ask. All right. So these are the new functions we're going to form out of two existing functions. And I'm just going to go ahead and do a couple examples where I give you f and g, and I ask you for some of the combined functions and their domains. So I want to find f plus g, f times g, f over g, and then finally f circ g and their domains. So first there's the algebra question. Can we find a formula for these new functions in terms of the old functions? And then the second kind of question is, can we find the domain of each of those new functions? F plus g first. Well, f plus g of x is f of x plus g of x. I will tell you this very first step on all these problems, this is the crucial thing. Go from this to this. Then you can follow your nose. I'm going to refer to this as setting up the problem or writing it out schematically. You must do this. If you do this first, I promise you, you will get good at these. If you don't do this, if you skip this, you'll run into trouble on these harder problems. I promise you. So please always start by writing these out schematically. I swear, even though it feels silly, it will save your ass at least once in this course. All right, f of x is 1 over x minus 2, and g of x is the square root of x. So this is 1 over x minus 2 plus the square root of x. Okay. I would like to find the domain. We could put these into a single fraction if we want to, but we don't have to. I just want to find the domain. So are there any domain red flags?
Variable in the bottom.
Excellent. Yeah. Erica sees the variable stuff in the bottom. Any other domain red flags?
Under the square root.
Yeah. The variable's under an even root. So the variable stuff downstairs, I know that x minus 2 is not allowed to be equal to 0. So x can't be equal to 2. And the variable stuff under the radical, I know that the stuff underneath the even root here isn't allowed to be negative. I know I need x to be greater than or equal to 0 because that's the thing that's under the radical. So if you draw this stuff on the number line, here's 0, 2. I know I need my shit to be first not equal to 2, so I gotta punch out the 2. And I also need all my shit to be bigger than or equal to 0. So if you kind of shade that inequality, and then hop over the 2 here, that shaded set is my domain. So that's bracket 0 to 2 parentheses union with parentheses 2 to infinity. Y'all see it? Here's the bracket 0 to 2 parentheses piece. And here's the parentheses 2 to infinity piece. So that's it. This is your domain. Any questions about how we're finding that domain? Okay. Next, we want to find f times g and its domain. So f times g of x schematically, that's f of x times g of x. That means f of x is 1 over x minus 2 times g of x is the square root of x. And here, these are simple enough to combine into a single fraction. This is the square root of x over x minus 2, right? Because the square root of x is square root of x over 1. So multiplying those fractions, that's easy, and it's nice. We should do it. Any questions about how we arrive at this? Okay, domain red flags.
Variable downstairs.
Yep. And
Cannot equal.
Roots.
yeah, very good, very good. So like Eric is saying, variables downstairs, so this can't be 0. And I think Hugo was saying the root. We got right. It's the same shit, isn't it? It's the exact same shit. This function has exactly the same issues that this function has. I mean, not just the same red flags, but even like the same details of the red flags. Yes, there's variables downstairs in both of these, but it's the exact same variable stuff. And there's variables under radicals in both of these, but it's the exact same variable stuff. It's the exact same shit as f plus g. So, same domain. Don't worry, these won't all be the same. In fact, this next one is going to be a little different. All right, let's look at f over g. F over g. Now here you've got a couple challenges. You've got some kind of compound fractions. Because you're going to take f of x and divide it by g of x. Remember, you got to start out just writing down what the formula tells you. What does the formula mean? That's what it means. Okay. Write that shit out. And then we're going to try to plug in. So always, your very first step should always just be to write out the definition. Now, f of x is 1 over x minus 2. And I'm dividing that by g of x, which is the square root of x. I know fractions are intimidating. And this is one of these places where we need, like, coming into Calc 1, got to be a badass with fractions. I know you can kind of squeak through college algebra without fully understanding this stuff, but here you've got a fraction with 3 pieces. This middle bar is kind of the big boy bar. This is the top, this is the bottom. So I would encourage you, just like we did when we talked about that difference quotient stuff, remember the top and bottom, always think of them as being in parentheses. And this bottom, this is really root x over 1, right? Anything is itself divided by 1. This is the key to simplifying this, and you need to simplify this in order to get the domain right. So now we leave the top alone. And we flip and multiply. Another way to think about this is that dividing by the square root of x is the same as multiplying by 1 over root x. So I'm going to take this and divide by root x, which means I'm going to take this and multiply by 1 over root x. But I think most people get comfy like this. First questions about the algebra here. I have a fun question for you guys. Go ahead and launch a little poll here. It's anonymous. Does this function have the same domain? Same red flags, right? Variable stuff downstairs, variable stuff under the radical, and it's the same shit. Got 8 folks so far, 9. And waiting on one more. So the no's have it. This is the result. And the people who voted yes have every reason to vote yes. The people who voted no, can someone explain to me why?
I put no because you could still, for the under the square root, put like it could be 0. And then if you do 0 times that, that can make it all 0 under the fraction.
That's excellent. So the domain from the previous 2 steps was bracket 0 to 2, parentheses, union, parentheses, 2 to infinity, parentheses. So which piece is going to change?
The bracket.
Yeah, this bracket right here is about to become a parentheses. See, this set includes 0. It's okay for me to plug 0 in here. I'd have 1 over -2 plus 0. Right? The square root of 0 is 0. So if I plug 0 in here, no problems. I get -1/2. I plug 0 in here, no problem. I get the square root of 0 over 0 minus 2. Again, the square root of 0 is 0, and the downstairs would be -2, so that's 0 over -2, which is 0. No problem there. But if you try to plug 0 in here, this first piece is -1/2. The second piece would be 1 over the square root of 0. And the square root of 0 is still 0. So this would be -1/2 times 1 over 0. 1 over 0 is not defined, right? The thing here is that this guy right here is actually 2 red flags at once. He's variable stuff under an even root, but he's also extra variable shit downstairs. So the domain here is parentheses 0 to 2, union parentheses 2 to infinity. I need this to not be 0, and I need this to not be 0, because they're both variable stuff on and downstairs in a fraction. In addition to that, I still need this x to be greater than or equal to 0 because it's a variable under a square root. Questions about the domain in this third piece? I want to point something out. If you simplified this wrong, if you like flipped this and brought this upstairs or something, you would get a totally different domain. So the algebra, cleaning this up correctly, is very much important here. So as you're working through the homework, practice with your fractions. I know it might feel silly to say that with grown-ups, but you really do need to get comfortable working with fractions, and not just in terms of numbers, in terms of algebraic expressions. If you're having any trouble with that, come by office hours. I'll tell you, I'll be honest. I struggled with some of the concepts in this until about the second week of Calc 1 when I was a student back, a million years ago, whatever. I still had some uncertainty about what to do with some kind of mixed fraction pieces. And I want to make sure you don't suffer the way I suffered. It caused me great pain until I got it sorted out, which I finally did. And now I'm here to help you not have that pain. So here's my domain. One more thing to do here, and that's the composite function, f of g. So last call for questions on any of these first three. Show the solutions. Okay. The last thing we wanted to find was f of g, or f circ g, and its domain. I'll remind f is 1 over x minus 2. G of x is root x. And now we wanted to find this guy and its domain. So we'd start by saying, okay, well, let's find a formula for f circ g of x. And just like with the last three, the only appropriate place to begin is with the definition. This is f of g of x. And you start with the inside. It's f of something, so at some point I'm going to use this formula, but f of what? Well, it's f of g of x. And g of x is the square root of x. This is f of the square root of x. So this is the definition, just like writing f plus g of x equals f of x plus g of x. This is the definition. And then the inside piece here, g of x, I know what that is. G of x is the square root of x. And now finally, I can use this formula. F of anything is 1 divided by that thing minus 2. So f of the square root of x is 1 divided by the square root of x minus 2. Just like f of dog shit would be 1 over dog shit minus 2. So here's the first part done. Found the formula for f circ g. Let's find the domain. Looking for red flags. And again, we've got both of those same sort of red flags. I've got some variables downstairs. And I've got variables under a radical. But this time it's a little different. The variable stuff I have downstairs is root x minus 2. So I need to make sure that thing is non-zero. Which means the square root of x, just add 2 to both sides here, has to be different from 2. And then if you square both sides, see that means x has to be different from 4. So x here not allowed to be 4. And then the other thing is that since the x is the thing that's under the radical, I need x itself to be greater than or equal to 0. Alrighty, so what's my domain here? I need numbers bigger than or equal to 0, not equal to 4. I recommend plotting these on the number line. Can't be 4, so we're going to punch 4 out. Can be 0, 0 is fine, and anything in here is good. Anything bigger than 0 is fine. Anything bigger than 4 is fine. Anything between 0 and 4 is fine. I can't come over here because these are not satisfying this condition. And I can't have 4 in there because x is not allowed to be 4. So this would be bracket 0 to 4, paren, union, paren 4 to infinity, kind of like the first one. Instead of a 2, now we have a questions on this example, any one of these last 4 parts?
Where did the 4 come from?
So I'm making sure that the piece downstairs here is not equal to 0. And to figure out what I need to do to make sure this isn't 0, I'm working with this expression here.
Okay.
Now I'm writing the not equals, and that's the idea because I want this to not be equal to 0, but you can do the same operations that you would do for an equal sign. So from here to here, I added 2 to both sides. And then from here to here, I squared both sides. But if you wanted to just set this up and solve it like a regular equation, you could do that too. You could just say root x minus 2 equals 0. Just remember in your head that you need to kick the solutions to that equation out of your domain. So, does that make sense?
Yes, yes, yes.
Cool. So if I plug 4 in here, then this whole thing is 0. That's bad because it's downstairs. All right, that's sort of the nuts and bolts of the first part of this section. In addition to nuts and bolts stuff, I want to talk about some kind of more abstract stuff. So mapping diagrams and machine diagrams are different ways you can think about a function. And they both have some utility here. So we haven't really talked about machine diagrams. I want to introduce that concept. My dog just farted. That reminds me of an analogy. A machine diagram is a way of describing a function kind of in terms of an assembly line or a machine. A function takes something in as its input, it messes with it somehow, and then spits something out as an output. Schematically, we can represent that as like a little box. I'll call this the F machine. It's going to take in x's. It's going to spit out f of x's. So you can kind of think of this as being a machine in a factory, right? Like, you know, empty soda bottle comes in, the machine fills the soda bottle, full soda bottle comes out. Right, that's actually a function. It is, it's a weird function, but it's a function. In mathematics, the functions we use are mathematical. So like a number will come in, and then f will do something to that number, and then something, you know, it's usually another number will come out. So like maybe f is the squaring function, and a number comes in like 2, And f squares that number, so 2 squared, or 4, comes out. Just an analogy, way to think of functions. So the function f can be thought of as a machine. Think of functions as machines. They take in an input, input side, and this is the output side. So inputs, x's come in, f does something to them, and then outputs, f of x's, come out. Machine diagrams are useful for understanding that last operation, the composite operator. Here's a gross analogy. I just lots of gross analogies in my head today. You guys seen the human centipede?
Yes.
A double underlying gross analogy. The composite operator is the human centipede of function machines, or machine diagrams. Composite operator, that's the F circ G or fog thing. This is the human centipede of functions. Okay, what I mean by that is you take the output from one and you hook it up to the input of the next one. I know it's gross. So here's the G machine. X's come in, G of X's go out. Here's the F machine. Normally, the F machine, X's come in, F of X's go out. But I'm going to hook the mouth of the F machine up to the output of the G machine. So G of X's are what's coming in now. And F is going to do what it does. You feed it something, it F's that thing and sends out F of that thing. So if I feed the F machine G of X's, what's going to come out is F of G of X. And that's it. That's what comes out here. This whole thing, right here is the F of G machine, or the fog machine, if you're silly about it. So you stitch the two together like a human centipede. That's what function composition is. X's come in, G gets done to X's, so a G of X's are produced. Then those are fed as the input to the F machine. F does whatever it does to the G of X's that come in, and what comes out is F of G of X. So if G is the square root function, and F is the function that adds 7, then X comes in, G takes the square root of X, and then F adds 7 to that. F circ G would be the square root of X plus 7. A less gross analogy in terms of something called a mapping diagram. We talked about mapping diagrams back on the first day of class. So over here is the domain of G. Here's the range of G. So this takes in some X over here, and it maps that to G of X over here. If I then treat that as the input space for the function f, then what I'm going to have over here is f of G of X. And this whole thing together would be the f of G map, taking you straight from X to f of G of X. Oops, sorry. So two kind of ways to think about composite functions in the abstract. I like the machine diagrams. I think these are probably the most useful way to do it. You can see that the domain of f circ G, the composite, has to come from the domain of G. Both of these do a good job of illustrating that G is actually what happens first. Even though when you write f circ G like this, it looks like the G comes last. The G is actually what happens first, right? The X's come in, G happens, then some shit gets spit out into the F machine, F happens, then you get f of G out. In both of these cases, you see that G is actually the thing that happens the first time. And then you take the output from G and you use that as the input for F. That's what's going on. That's all pretty abstract. There are really good reasons for you to need to think about this stuff in this way, though, because when we talk about inverse functions, inverting a function, that's all done in terms of this algebra. Even better, if you're going to go to graduate school for mathematics or anything intensely mathematics related, you're going to study algebras of functions. And in those sort of spaces where you study algebras of functions, instead of like right now, all the algebra you guys do is algebra of real numbers. That's what we're doing. In this pre-calculus algebra class, the objects to which we are doing algebra are numbers, real numbers, right? Our variables all represent numbers. In slightly more grown-up math classes, we do algebra with all sorts of different shit. Example, can do algebra with Rubik's cubes, right? These things. These are algebraic objects. Can do algebra with whatever the fuck you want, vectors, matrices. We're going to talk about that a little later in the semester. One of the most important abstract algebras are function spaces, where the objects that your variables represent are functions instead of numbers. And in that setting, function composition is the thing that behaves like multiplication. It's very cool. It's very, very cool and very important in a surprising number of places, not just in mathematics, physics, chemistry, astronomy. So this is an exciting thing to talk about. Now for us, again, the real reason you need to be comfortable with these diagrams and what they mean is because in the next section, we're going to talk about how to invert a function. That's going to mean like, how do I take this G machine and run it backwards? And in order to do that, we're going to use this operator to define something called the inverse of a function. Nothing to do with 1 over the function, not inverse like that, not like 3 1/3, totally different, but like square and square root. But that's for next time. For this time, I think we are about done. There's not a whole lot more that I want to kind of bludgeon you with, and we don't really have enough time to go into the inverse stuff in a lot of detail. So I'll go ahead and end it here for today. I think I'm supposed to let you guys go at 2:50 anyway, right? We're close to that now, yeah. 2:47, yeah, perfect. All right, so I'm gonna go ahead and conclude class here for today. You're gonna see a new homework open up. You're gonna see a quiz open up. Please attempt the quiz no later than next Thursday, preferably before 3 p.m. That way you can come talk to me in the office hour if you're having any trouble with it, but it won't be due until next Monday. And next Monday is also the day of your first test. So do the quiz first. Think of it as like a preparation for the exam. Ideally do it in time so you can come talk to me in office hours beforehand. But if you don't get to the quiz until Saturday or something, you can send me an email. You can be like, hey, I really had trouble on this part of the quiz. I'm worried about it showing up on the test. Here's my work. Send me a picture of the work, and I'll give you some suggestions, some guidelines, things you can do to improve or whatever. Any questions for me?
Thank you, Professor.
Of course. All right. So remember, no class tomorrow. College is closed. Instead of having exam 1 on Thursday, exam 1 is next Monday. There's going to be one more homework set and one more quiz due by that day. And please, I suggest you attempt the quiz before Thursday so we can talk about it. That's it. I hope you guys have a lovely rest of your day. Stay safe with this storm. I'll see y'all on Thursday.